studying total solar eclipses have revealed some of the most fundamental discoveries in science today. During these celestial events, scientists discovered the sun structure, the first proof of Einstein's theory of general relativity, and the element helium 30 years before it was found on Earth. They also discovered huge solar explosions called coronal mass ejections, eruptions on the sun that continue to be an important component of NASA's research. Coronal mass ejections, or CMEs, are giant eruptions made up of hot gas and plasma. From the sun's surface, they propel immense clouds of solar material into space, speeding at up to 1 million miles per hour and carrying enough energy to power the world for 10,000 years. Sometimes they're directed towards Earth when they can affect our planet's space environment, causing space weather. Scientists track and study CMEs because they can trigger global changes in Earth's magnetic field. When intense, these can create magnetic storms that can cause aurora, but can also affect satellite electronics and power grids on the ground. Scientists discovered these eruptions in the 1970s during the beginning of the modern satellite era, a time when satellites in space were able to capture thousands of images of solar activity that had never been seen before. But in hindsight, these might not have been the first time scientists had noticed these solar features. Soon after they discovered CMEs, scientists came across reports of a total solar eclipse in 1860 that looked very similar to their satellite images. On July 18, 1860, the shadow of the moon travelled over North America, Spain, and North Africa before departing Earth. Much of the path of totality travelled over populated land, resulting in a wealth of observations. Back then, astronomical photography was still new, so many scientists recorded their observations by hand. The drawings show the large white fingers of the corona, and also a distinctive arc-like feature. With multiple images drawn from different locations across Europe, it appears to evolve over time. But not all the images showed this. About 2/3 of people saw the tulip head-like shape, but 1/3 didn't see anything at all, including renowned scientist Angelo Secchi. It wasn't until over 100 years later, with regular satellite imagery, that scientists reopened the debate about what was seen in the 1860 eclipse. The strong resemblance shows that this eclipse may be the first record of a CME. While satellites in the space age exploded the field of CME research, total solar eclipses seen from the ground still provide unique views of the sun's atmosphere that help our understanding of what causes these explosions. Current instruments in space studying the corona need to block the sun's bright body with an occulting disk. The disk covers up the sun and a portion of the lower corona, an important region that scientists believe is responsible for accelerating CMEs and forming solar wind. So when eclipses happen to fall on land, scientists take advantage of these rare events. With each new total eclipse, there's the chance for new information and new research, and the chance to reveal something as astronomical as the first CME.
as the darkness slowly encroaches. Do not fear. The sun will shine again. On August 21st, a total solar eclipse will cross the United States from Oregon to South Carolina. And for a couple of minutes, day will turn into night. Enjoy the show, but don't look at the sun. The only safe time to view an eclipse is if you're in the path of totality and during the minute.
The television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA television.
August 2017, a big month for astronomy. Presented by Science at NASA. Sky watchers in the United States have been waiting for this date for years. On August 21st, 2017, there's going to be a total eclipse of the sun. With the path of totality stretching from Oregon to South Carolina, people can see the eclipse from coast to coast. The timing of the eclipse will provide the opportunity for viewers to see one of the biggest astronomical events of the century, just a few weeks after enjoying one of the biggest meteor showers of the year. Every August, Earth passes through a stream of debris from Comet Swift-Tuttle, source of the annual Perseid meteor shower. This year, the shower will peak on the nights of August 11th, 12th, and 13th. Although the comet is far away, currently located beyond the orbit of Uranus, a trail of debris from the comet stretches all the way around its orbit, back to where it nears Earth's orbit. As our planet crosses the debris zone, the upper atmosphere will be pelted by specks of comet dust traveling 132,000 miles per hour. At that speed, even a flimsy speck of dust makes a vivid streak of light when it disintegrates, a meteor. Because Swift-Tuttle's meteors streak out of the constellation Perseus, they are called Perseids. Astronomer Bill Cook of NASA's Meteoroid Environment Office offers these observing tips. If it's not cloudy, get away from the bright lights, lay on your back, and look up. Remember to let your eyes get adjusted to the dark. It takes about 30 minutes. You'll see more meteors that way. You don't need to look in any particular direction. Meteors can generally be seen all over the sky. Not all the meteors you'll see belong to the Perseid meteor shower. Some are sporadic background meteors. Others are weaker showers also active in August, including the Alpha Capricornids, the Southern Delta Aquarids, and the Kappa Cygnids. But the vast majority will be Perseids. Cook says if you see a meteor, try to trace it backwards. If you end up in the constellation Perseus, there's a good chance you've seen a Perseid. Under ideally dark skies, observers can often see dozens or even more than 100 Perseids per hour when the shower peaks. This year, the glaring light of a bright, waning gibbous moon will interfere, reducing the number of visible meteors. Now for the good news. That same moon is heading toward the sun, narrowing as it goes until the thinning crescent disappears into a black disk that will perfectly cover the sun on August 21st. A meteor shower, followed by a total solar eclipse. August doesn't get much better than that. For more news about backyard astronomy, stay tuned to science.nasa.gov.
Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television.
A solar eclipse occurs when the moon moves between the Earth and the Sun, blocks the Sun's light, and casts a shadow on the Earth. When the moon completely covers the bright disk of the Sun, That's a total solar eclipse, and it happens roughly every year and a half somewhere on Earth. A partial solar eclipse is more common, happening at least twice a year. A lunar eclipse, on the other hand, is where the moon moves behind the Earth, so it's now the Earth blocking the sun's light on the moon, creating a shadow on it with a red tint. The easy way to remember the difference is to remember what gets darker. With the solar eclipse, the sun gets darker, and during a lunar eclipse, the moon does. A solar eclipse is a rare event that not many get to see, because the moon's shadow is relatively small. This limits the locations on Earth that get to see it. You have to be on the sunny side of the planet, and you have to be in the path of the moon's shadow. So, if you find your area in the path of totality one year, you've hit the jackpot, because on average, that same spot on Earth will only get to see a solar eclipse every 375 years. During a solar eclipse, the moon casts a shadow with two parts, the umbra and penumbra. The moon's umbra is part of the moon's shadow where the entire sun is blocked by the moon. In space, it's a cone extending some 400,000 kilometers behind the moon. It's when the small end of this cone hits the Earth that we experience a total solar eclipse. Most eclipse maps depicting the path will show you a circle representing the shadow of the moon, but in actuality, the true shape of the umbra is more like an irregular polygon with slightly curved edges. This is because the moon isn't a perfect circle. It has mountains and valleys on its surface, which all affect the passing sunlight and subsequent shape of its shadow. And scientists now have a greater understanding of the shape of the moon's surface, thanks to NASA's Lunar Reconnaissance Orbiter. Topographic maps, photos, and other datasets has allowed us to more precisely pinpoint the regions on Earth falling within the path of totality of a solar eclipse. So, if you get the chance to witness a solar eclipse, always remember that our little moon plays a role that's quite large.
What's up for August? August 21st's total solar eclipse traces a narrow path across the nation, though most of the U.S. will see a partial eclipse. Hello and welcome. I'm Jane Houston Jones from NASA's Jet Propulsion Laboratory in Pasadena, California. Not everyone can travel to the narrow path of totality, so here are some things to look for no matter whether you see totality or a partial eclipse. Before Eclipse Day, pack your Eclipse toolkit with a notebook, pen or pencil, a clock, a stopwatch, the front page of a newspaper, a thermometer, and a stick with a piece of crepe paper tied to it. And bring an assistant to help conduct some science observations. Practice using a citizen science phone app to help you study clouds, air, and surface temperatures during the eclipse. A good one is the Globe app. Go to the location where you'll view the eclipse and check for trees and buildings that may obstruct your view. Totality lasts less than 3 minutes, so you may want to focus on doing only one science observation, or just really experience the eclipse. Don't waste this once-in-a-lifetime opportunity by watching it on your phone screen. Plan to have your safe solar viewing glasses within immediate reach, in your pocket or around your neck for quick eye protection before and after totality. Just before totality, if you have a good view of the horizon, look west for the approaching shadow. After totality, look east low on the horizon for the departing shadow. If it's cloudy, try to see the shadow by looking up at the bottoms of the clouds. During totality, look for stars. Can you see Regulus in the solar corona? The stars of Orion? How early and how late is Venus visible? Can you see any other planets? Before and after totality, you may see moving waves of light and shadow, like the patterns you see on the bottom of a swimming pool. How dark does it get at totality? As it gets darker, look at the newspaper you brought and see what's the smallest print you can read. How much does the temperature drop during totality? Does the wind start, stop, or change direction? Watch and listen for changes in animal and bird behavior. During the partial phases, use your hands as a pinhole projector. You'll be able to see the crescent shape of the sun projected through the spaces created by your fingers. You can also make a paper pinhole projector. In fact, any item with one or more holes in it, like a kitchen colander, a loosely woven straw hat, even leaves on trees, will project the crescent shapes. You can find out about all of NASA's missions at www.nasa.gov. And you can find out more about the Eclipse, including Eclipse safety, at eclipse2017.nasa.gov. That's all for this month. I'm Jane Houston Jones.
There are two important things to remember about watching a solar eclipse. The first one is never look at the partial eclipse that comes before and follows after a total solar eclipse. Even if 1% of the sun is showing around the edge of the moon, that's too bright for your eye to handle. It will damage your vision. The second thing, however, is do look at the total solar eclipse with your naked eye. Your eye is an amazing device and will show you lots of detail during totality. Today, I'm going to show you several techniques for viewing a partial solar eclipse. The first one is to go online and to buy a pair of solar viewing glasses. These have been designed to block the sunlight during a partial eclipse or even the full sun so that you can look at the sun with your naked eye. The second is to go to a welding shop and get a number 14 welder's glass. This blocks enough of the sunlight that you can look at it safely with your eye. A third technique will be to make a pinhole in a piece of cardboard and then make a pinhole image of the sun. And the fourth technique, which we'll take you through today, is to use a small telescope, a spotting scope, or a binoculars to make an image of the sun projected onto a white piece of cardboard. This was the technique used by Galileo himself. All of these will allow you to watch the partial solar eclipse and save your eyes.
Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television.
The most amazing thing was when I was in Turkey in 2006 and I saw a total solar eclipse live and in person.
I am just getting chills, literally and figuratively, about the excitement of this amazing spectacle.
As an astronomer, I felt lucky enough to be witnessing the fact that we are part of a moving solar system in which you have the Earth, Sun, and Moon interacting together. As a person, I felt very moved when I saw totality in the middle of the day. Totality is when the moon covers completely the sun, and so all the light that we normally see during the day from the photosphere of the sun completely disappears, and the only thing that you are left seeing is a dark sun, completely blackened, and then on the outside of the sun, the corona is visible. So we're going to show you what happens to create totality, to create this darkness in the middle of the day on the Earth's surface as a result of a total solar eclipse. So basically I have a fictitious sun behind me, which is a light source, pretending that it's the sun, and we have the Earth and we have the moon. So the moon actually travels in front of the Earth, covering the sun, and that's what causes the total solar eclipse. Did you see that shadow, Lily?
I did.
There it is.
It's
So
amazing.
basically that shadow creates what is called a path of totality, which will be a strip of darkness. This is not exactly to scale, but it is helpful to see. It's very simple. The shadow of the moon is cast upon the surface of the Earth. The moon is indeed much smaller than the sun. 400 of these little moons will actually cover the diameter of the sun. But the moon is also 400 times closer to us, and that is what creates the total solar eclipse, which is an amazing cosmic coincidence. So to illustrate what I'm talking about, I'm going to use my thumb, which is much smaller than your head, to try and cover it. So if I try to cover it here, I close one eye, you're still very visible. But if I bring my thumb very close to my eye, eventually your entire face is actually covered. And that is what's happening. And you can try this at home. Do that with different objects and different distances using your thumb and closing one eye, and you'll be able to understand why the moon, which is 400 times smaller than the sun, but is 400 times closer to us, can actually cause the sun to be completely obscured in a total solar eclipse.
If the moon goes around the Earth once a month, how come we don't have an eclipse every month?
The orbit of the moon around the Earth is actually slanted, so most of the time the moon will actually travel above the plane of the Earth and the Sun line or below the plane of the Earth-Sun line and not cause an eclipse. We are not going to have a total solar eclipse forever. And that is because the moon is actually receding from the Earth. The distance is actually increasing due to tidal forces. And so, of course, as the moon recedes from the Earth, it covers a little bit less and less of the solar disk during an eclipse. But this will happen in 500 million years. So we still have time to go out there and catch a beautiful total solar eclipse.
As the darkness slowly time to view an eclipse is if you're in the path of totality and during the minutes of totality. Otherwise, you'll need certified eclipse glasses. To learn more, go to eclipse2017.nasa.gov and NASA TV.
Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television.
On August 21st, 2017, a solar eclipse will pass over all 50 United States. This will afford most of the country a glimpse of what it is like to have the moon slide between the sun and the Earth, casting a shadow on us down below. The experience will look different depending on where you are located. If you are along the path of totality, you see the moon fully block the sun. If you are outside of the path, you will see the moon go by, but the sun will never be fully covered. Wherever you are, you never want to look directly at the sun without protection. Like eclipse glasses, not sunglasses. The one exception is if you are able to see totality. Only when the moon has fully blocked the sun, you are safe to look at the eclipse directly. Before and after that moment, keep your eyes protected. Events like this are rare.
The last total solar eclipse to cross the U.S. coast to coast was in 1918. And the next total solar eclipse in the continental U.S. isn't until 2024.
Don't miss this opportunity to experience a solar eclipse.
Space Place. In a snap. Whoa! It's the middle of the day. So why is the sky getting dark? It's a solar eclipse. A solar eclipse happens when, at just the right moment, the moon passes between the sun and Earth. Sometimes the moon only blocks part of the sun's light. This is called a partial solar eclipse. Other times, the moon blocks all of the sun's light. This is called a total solar eclipse. As the moon blocks the sun's light, it casts a shadow on part of the Earth. The moon's shadow creates a trail as the Earth rotates. This trail is called the path of totality. If you want to experience total darkness during an eclipse, you have to be in the path of totality. In that path, the moon completely blocks the sun's light for a few minutes. It gets so dark that it looks like nighttime during a full moon. If you don't know what's happening, it can be confusing. Animals can get confused too. But this total darkness can also be kind of cool for scientists who study the sun's atmosphere, called the corona. The corona is very dim. It's usually hard to see because the sun is so much brighter. But when the moon blocks the sun's light during an eclipse, all you can see is the light from the corona. Total solar eclipses over the land, where people can see them, don't happen very often. But when they do happen, the moon gives scientists, and the rest of us, a glimpse at the corona's beautiful streams and ribbons. Thanks, Moon!
Find out more about the sun at NASA Space Place.
Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television. Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television.
What we're talking about is several visualizations of the path of the moon's shadow during the eclipse in 2017. Everything in it is driven by the data. So the color of the ground, the position of the path of totality, the lighting from the sun angle, all of those are things that are based on data. A lot of NASA products were used to create this visualization. I used the Lunar Reconnaissance Orbiter, the laser altimetry data from that, which gives us a digital map of the elevations on the moon. For the Earth, I used something called SRTM. This was a radar that was flown on the space shuttle. For the positions of the Earth, the moon, and the sun, I used a JPL ephemeris. An ephemeris is just a list of positions, but it's the most accurate tabulation of those positions. This visualization is unique because it shows the effect of both the irregular edge of the moon, the limb of the moon we call it, and the elevation of the observer. Now, we've known for a long time that the elevation of the observer affects where the shadow is, and we've also known that the mountains and the valleys along the edge of the moon affect the shadow. So you may have seen on eclipse maps in the past that the image of the umbra, that shape of the shadow on the Earth, is drawn as a smooth oval. But we know that the moon isn't smooth. Around the edge of the moon, we have these sort of jagged peaks and valleys. And a peak can block the sun a little bit earlier than you thought, and a valley can let the sun in a few seconds longer than you thought. The combined effect of these peaks and valleys is to create a shape that's not really an oval, it's more like a polygon. But it hasn't actually been seen in exactly this way before, where we calculate those circumstances for every point on the map and draw that shape. Totality is that 2 minutes when or 2.5 minutes when the moon completely covers the sun. The sudden darkness of totality is just something that a lot of people can't compare to anything else. I love the idea that I'm giving this kind of map to other people, and especially that it's more detailed and more accurate so that people are actually in the right place to see it.
Watch NASA Television's pre-show coverage at 12 p.m. and the entire total solar eclipse coverage through the eyes of NASA at 1 p.m. Eastern, only on NASA Television.
Looking back at Earth from a million miles away, the Deep Space Climate Observatory will watch the August total solar eclipse in real time, giving scientists a unique opportunity to study our solar-powered planet. NASA's Earth Polychromatic Imaging Camera, called EPIC, will capture images of the moon's shadow passing over Earth. A team of scientists will combine data from EPIC with measurements taken on the ground to learn more about how the sun's energy is absorbed and reflected in Earth's atmosphere. Clouds affect how much of the sun's energy reaches Earth, which can be difficult to calculate without knowing how each cloud blocks, absorbs, or transmits light. Like a giant cloud, the moon blocks out the sun's energy during the solar eclipse. Because we already know the exact shape and makeup of the moon, scientists can use the natural phenomenon to develop new calculations that could improve estimates of Earth's energy system and answer questions about Earth's climate. NASA has studied the Sun and Earth relationship for more than 40 years. This year, NASA is launching 2 instruments to further study Earth's energy system.
Studying total solar eclipses have revealed some of the most fundamental discoveries in science today. During these celestial events, scientists discovered the sun structure, the first proof of Einstein's theory of general relativity, and the element helium 30 years before it was found on Earth. They also discovered huge solar explosions called coronal mass ejections, eruptions on the sun that continue to be an important component of NASA's research. Coronal mass ejections, or CMEs, are giant eruptions made up of hot gas and plasma. From the sun's surface, they propel immense clouds of solar material into space, speeding at up to 1 million miles per hour and carrying enough energy to power the world for 10,000 years. Sometimes they're directed towards Earth when they can affect our planet's space environment, causing space weather. Scientists track and study CMEs because they can trigger global changes in Earth's magnetic field. When intense, these can create magnetic storms that can cause aurora, but can also affect satellite electronics and power grids on the ground. Scientists discovered these eruptions in the 1970s during the beginning of the modern satellite era, a time when satellites in space were able to capture thousands of images of solar activity that had never been seen before. But in hindsight, these might not have been the first time scientists had noticed these solar features. Soon after they discovered CMEs, scientists came across reports of a total solar eclipse in 1860 that looked very similar to their satellite images. On July 18, 1860, the shadow of the moon travelled over North America, Spain, and North Africa before departing Earth. Much of the path of totality travelled over populated land, resulting in a wealth of observations. Back then, astronomical photography was still new, so many scientists recorded their observations by hand. The drawings show the large white fingers of the corona, and also a distinctive arc-like feature. With multiple images drawn from different locations across Europe, it appears to evolve over time. But not all the images showed this. About 2/3 of people saw the tulip head-like shape, but 1/3 didn't see anything at all, including renowned scientist Angelo Secchi. It wasn't until over 100 years later, with regular satellite imagery, that scientists reopened the debate about what was seen in the 1860 eclipse. The strong resemblance shows that this eclipse may be the first record of a CME. While satellites in the space age exploded the field of CME research, total solar eclipses seen from the ground still provide unique views of the sun's atmosphere that help our understanding of what causes these explosions. Current instruments in space studying the corona need to block the sun's bright body with an occulting disk. The disk covers up the sun and a portion of the lower corona, an important region that scientists believe is responsible for accelerating CMEs and forming solar wind. So when eclipses happen to fall on land, scientists take advantage of these rare events. With each new total eclipse, there's the chance for new information and new research, and the chance to reveal something as astronomical as the first CME.